Hi everybody, we are Marco, Lara and Irene from BEye team. In this video we are going to show what kind of challenges our project faced and our solution for the implementation of a retinal vessel segmentation algorithm on an FPGA. As shown in our previous video, our algorithm is composed by a series of processing steps. The first is a pre-processing phase consisting of a median blur filter. The vessel detection step performs a matching filter using different kernels that applied a Gaussian blur and an adaptive threshold to classify the pixel as vessel or background. A blob detection and removal algorithm is then applied to remove false positive from the obtained results. Finally, a median and Gaussian blur are used to enhance the final result image. Most of these different methods are an example of convolution filters, so we are going to explain their implementation first. The implementation of convolution filter in hardware presents a series of challenges, including their 2D nature, which can prevent from using a streaming architecture, the need to store the image to perform the convolution on a sliding window using nested for loops, and the presence of a high number of direct access to memory, which causes high latency. Our design allows to perform a general convolution filter without these drawbacks. It is composed by a line buffer which stores the needed line on the image and a sliding window used for the convolution function. The input is stored in the line buffer and a column is transferred to the window on each clock cycle. From the window, the result value is computed with the convolution function, which is different based on the different filter to implement. In order to achieve higher performances, special data structure and optimization have been used. The line buffer is implemented with Xilinx Video Library Structure HLS line buffer, which makes it easier to implement the buffer without caring about the particular operation, such as shift or inserting of pixels and lines. To improve the buffer speed, it has been synthesized on BEye blocks, one for each buffer line, to allow data access in just one clock cycle. To do this, a HLS-specific pragma, which is a array partition, has been used. The sliding window has been implemented using HLS window, which takes care of column shifting. To speed up this data structure, array partition has been used, but with a different dimension, transforming the window's pixel into single register. In this way, no access conflicts are present, and the pixel can be accessed in a clock cycle, while with BEye, just one pixel for line can be used at one time.
To improve the general performances of the filter core, two other pragmas has been used. HLS pipeline allows to perform loop pipelining. With this optimization, one loop step is performed for each clock cycle. This allows to filter to the entire image in a time linearly dependent by its size, and thus increasing the core's throughput. HLS unroll allows to perform loop unrolling, which is needed to improve internal loops, such as the convolution one, in order to be pipelined. The second kind of implementation core is blob detector and filter, used to remove the false positive noise in the image. This noise is composed by a high number of small black dots, or blobs. Thus it is impossible to classify or remove based on their sides. Several issues arise when the implementation of a blob filter is done. First, blob detection requires a direct access to the neighbors of each image pixel in order to label the various groups, resulting in a random sequence of accesses. That is not easy to model on hardware architecture, which several memory contains. Pixels counting in each detected blob can be done after the detection, but this would result in another call and a double pass of the image. We need a faster approach to detected blobs in just one pass. Finally, blob removal has to be done after the detection step, and this leads to a more difficult synchronization between cores. To solve this issue, two different approaches have been used. The first one concerns to the detection step, and the second the blob removal phase. For the first image filter, which is the blob detection one, several optimization and tricks have been used. The group labels and the count are stored in different BRAM blocks to achieve a single clock cycle latency. Only the line above the current pixel is stored in BRAM in order to check the already labeled pixels. Finally, the arrays are loaded based on label conflicts. To simplify the label conflicts management, a double access method has been used. An array stores the different labels, and each one can be linked with just another. So the stored value is the other label's value or not. In this case, is set to 0. The counts array is updated based also the label buffer. In case of a conflict, the label is invalidated and its counts are transferred to the upper label. Finally, the current pixels label is updated and the last group's label is linked in the upper one, in order to create a link that will be used also later in case of other conflicts. For remover paths, an additional couple of EP core and DMA is needed, because all the groups must be labeled before removing them based on counts, because the image cannot be stored entirely on block RAMs, but it must pass through CPU and central memory in order to be sent later to the last core. The pixels are directly blanked or filtered by checking the first pass output, which is the group pixels count. In this way, line buffer and sliding windows are not needed, saving the BRAM and flip-flops resources. Thanks for watching. You can contact us using emails and social networks. Please like and follow us on Facebook and Twitter. Stay tuned for the other updates.